Let's talk about computing volume using the method of cylindrical shells. So the formula for the cylindrical shell method is to integrate 2 pi r h, where r and h are the radius and vertical height of this cylinder that we're going to place into each of our shapes. The one thing to remember about these cylinders, or one of several things actually, is that the line of rotation, this axis of rotation in each problem always goes through the center of each of these shells. So that kind of tells you which orientation to stack them in, whether it's upright or to the side. Okay, so in all three of these examples, I'm going to be using the region between y equals 2x, the straight line, and y equals x squared, this piece of a parabola. So in a problem like this, they may not state what the x or y values involved are, and that's because these two curves intersect. You can sit there and brainstorm and see that they'll have the same output at 0 and 2. Or you could set x squared equal to 2x, put them together on one side and factor. But we can fill in either way that they'll intersect at x equals 2, y equals 4, and then also at the origin 0, 0. Okay, so in this first of the three examples with this same region, I'm going to rotate this about the y-axis. Right, so that kind of pins the region right here on the origin and spins it around. So it makes roughly this bowl shape that I have sketched out here. So again, this x value is 2. Over here, we would have -2, and that's probably sufficient. Okay, so the key to getting the R and the H formulas is to very carefully draw one shell inside this shape. All right, so I'm always very careful in this step because it's hard, and I always talk myself through it with the same couple of steps that I'll pitch to you here. Okay, so because the axis of rotation is vertical, we know that the tubes are going to go this way, so it's going to be upright the way I drew it here. So that means an x value is going to set the right edge, the right straight edge of this tube. So I'm going to pick an x value in my kind of original region area. So somewhere between 0 and 2, I'll throw an x. Let's say out here. And then I'm going to very carefully sketch the shell that would have that right edge. Okay, so above this x, I'm going to draw a vertical line in my picture above the x, and it has to only pass through the starter region, right? So the starter region is just between the two curves. So over here, my vertical line stays just between these two curves. That's the entire right edge of this shell. And that is good information to get me started. So what this cylindrical shell or tube is going to look like is the following. I've got kind of its symmetric match over here, and then it's going to wrap all the way around this way. It never has any thickness. It's just like a thin strip of paper that's like wrapping around. Okay, so we can see from this image now that we've sketched that shell carefully, the vertical height would be this distance right here, and then the radius of the tube is this distance here. Because it was an x value that defined this shell, it defined the right edge of the shell, that tells me that everything I'm about to do has to be in terms of x. So as soon as I make that call right there, I know everything is in terms of x. So if I need to say a vertical y distance, it's got to be a function x equal or y equals a function of x. Okay, so for this radius, let's start there. This radius is this horizontal distance from the y-axis out to this straight edge. And I did draw points that are right on the curves, but it's not actually going to either of the curves, right? Like I could draw this radius smack in the middle and just hit the vertical line. This distance is just the horizontal distance out to x, whatever it is. So in this problem, r is just x. In fact, anytime you rotate about the y-axis, the radius will just be x. The height does involve the curves that set the problem, which makes sense, right? They should both be involved somehow. So this height is the length of this side, which will be this y value minus this y value, higher minus lower. So it'll be line minus curve. So here the h is line minus curve. So it's each of their y values subtracting, but because we have to say it in terms of x, we get our formulas of x instead. All right, now that we have those choices, we can set up our volume integral, 2 pi r at h. So 2 pi r, and then h was 2x minus x squared dx. All right, and then the last piece of the puzzle here will be to put the bounds of integration. We know that they have to be x values because this is an integral all in terms of x. So the default is to just use the x values of the starter region, which are 0 to 2. They are going to be 0 to 2. The reason that that's what we're choosing is because 0 to 2 is it defines all of the shells necessary for the shape. So we just need to set one edge of each of the shells. So if you set just the right edges, it's 0 to 2. But that should always be from the starter region. All right, so for the sake of time, we're going to leave this here. So this integral represents the volume using cylindrical shells of that solid of revolution. If I actually was asked to fully compute this number, I would simplify the integrand before I did antiderivative stuff. So I would take the 2 pi, pull it outside the integral as a constant multiple, and then this x, distribute it into the parentheses so that what you have inside is just a polynomial. Then you're free to do reverse power rule for the antiderivative stuff. Okay, let's move on. So my second of the 3 examples will again start with that same little region trapped between x squared and 2x. But instead of rotating about the y-axis, we're going to rotate about the line x equals -1. It creates a very similar shape, but there's going to be some dead space in between, right? So as this region swings around -1, it's going to create kind of a tube down the middle of nothingness. Kind of here, like that. It does not have to be that good, just good enough. All right, it's a little wonky. The red line is supposed to be perfectly through the center, but this will work. Okay, so this is roughly my solid, and I'm going to do all the steps the same way. It's going to be really similar to the example above it, with just a difference in the radius choice. So this is a good one to practice our sketching the shell on. I'm going to pick an x value. So I know the tubes should go this way because my axis of rotation has to go straight through the center of the tube. So I know an x value will set the right edge of one of the tubes. So I'm going to pick an x value somewhere between 0 and 2 for this one. And above it, draw the right edge of the tube with a vertical line that is entirely contained in the starter region. So it has to be between the two curves. Just here to here. It can't go above this line or below this line because that would take me outside of the starter region. Exact same as the last example. All right, so now I am going to draw what I can of its little matching symmetric part over here, and that gets me started drawing my shell. Okay, so even though my image is a little wonky, we can still see the vertical height is right here, and then the radius is the distance from the center of the tube, the line of rotation, all the way to the edge of the tube. Right. Because x is what identified this one shell, this tells me the entire problem will be in terms of the letter x instead of 1. The height is the same as the last example. So the height is just this minus that, this y value minus that y value. So this will be the line minus the curve. What's different in this one is the radius computation. So it is a horizontal distance, so we're thinking x value. The problem is the x value that sets this shell is just this distance from here to here. It'll take you from the y-axis out to whatever x is. But that's not the radius distance anymore. The radius distance is that plus 1 to actually get to the center of the tube at -1. So here my radius is x plus 1. Okay. So we will then set up our volume formula, 2 pi r h. And then we set the bounds of integration. We know they should be x values because this whole integral is in terms of x. Again, your default can just be the x values of the starter region, 0 to 2. For this one, it seems a little fishy that it should still be 0 to 2, but if you think about it as the right edge of all necessary shells, there really wouldn't be any shells to the left of x equals 0 over here. Like there is no right edge of a shell here because this is all dead space. So because that starter region just didn't exist over here, there's no shells necessary in the next step. So that is the definite integral that represents the volume of this thingy. Okay, let's move on to our third and final example. This one, again, just uses the region between those same two curves, just because it's a good example. And for this one, we're going to rotate the other way, and it's going to change stuff. So this one will rotate about the x-axis instead. Okay, so we'll try to sketch this shape. Oh, I again know that they intersect at x equals 2, y equals 4. I'll label that for myself just in case. Go a little lower here. So on the outside, this will have straight edges. And then inside, it'll have a lot of dead space where this whole funnel shape here is empty. Okay, so this one, the tubes are oriented sideways instead of upright because the line of rotation has to go through the center of the tube, right? So my tubes are going this way instead. So that means that a y value is going to set one of those straight tube edges. So I'm going to pick a y value in here, and that's going to set the top edge of one of my tubes. Because I'm picking y right now to define a tube, that means the entire integral here is going to be in terms of y. So if I need to say a horizontal distance, I've got to back solve my equations. In fact, I might do that right now, right? So anytime I need to say a horizontal distance x, I'm going to have to give x as a function of y. So this will be root y equals x, and this will be a half y equals x. Okay, so we're going to carefully draw one of our cylindrical shells into the shape. Right at this y value, I'm going to draw a horizontal line that defines one flat edge of the shell. And again, just like before, it has to be completely contained within the starter region. So it's horizontal now, but it's still trapped within the initial shape. So just between the curves, just horizontal now. It'll have a matching edge over here, and I can start to draw it. So this is one tube or one cylindrical shell. Okay. So the height of this shell now goes the other way. This is the vertical height here, and this is our radius. Okay, let's start with the radius. This one, the radius of the cylindrical shell is the distance from the center line, x-axis, up to the horizontal line that we drew, right? It's not up to either curve specifically, it's this line, which is just the y value that you're at. And we are allowed to just say y here because everything's in terms of y. So my radius is just y. This will always be the case. Anytime you rotate about the x-axis, the radius is y. Anytime you rotate about the y-axis, the radius is x. Okay. For the height, the vertical height here, it's going to be the distance between these 2 points horizontally. So it's this x value minus this x value. You're subtracting them in that order, right minus left, because this is the bigger x value. This is the smaller x value. So it's going to be x value of the curve minus x value of the line. I'll write that over here, I guess. X value of the curve minus x value of the line. So this is where we're using our back solve formulas because we can't say x, everything is in terms of y. All right, and now I'm ready to go to my integral, 2 pi R, H. This is dy because everything's in terms of y. And that means that my bounds of integration also have to be in terms of y. So they're going to be the y values of the starter region, which was 0 to 4. 0 to 4 is it defines the top edge of all necessary cylindrical shells.